Calculus lesson on 3.8b, Newton's law of cooling. So the rate at which the object's temperature is changing at any given time is roughly proportional to the difference between the temperature and its surroundings. Okay, so if you sort of think about that, so rate of the temperature right here is roughly proportional to the difference, right? Yeah, so that's the key, right? Isn't it? So if you have dt, I know it's kind of weird. Capital T is the temperature and small t is the time, right? It's proportional to the absolute value difference between the two, right? Because surrounding temperature could be temperature could be either above or below, and this could even be true with free falling body. Let's say when on top of the plane or hot air balloon, you just jump off of it, and then it's just there's between just dropping something from there or throwing it down, right? So velocity may be different. So that's another problem that we could do. So that little squiggly little thing means that it is proportional to, and the way we write that from our algebra class is that dt is k times the difference. Guys, now can you do the difference, guys? Can we the separable equation? Why don't you guys go ahead and try to pause the video and see what you could do with it, okay? All right, guys. So let's move on to this, and what I have over here is, I worked it out for you already. There it is. There you go. So that right there is the general solution right there, guys. Okay. Yeah, the only difference between this and the ones that we have done in the past, that T sub s is constant. Capital T is not. That's a variable, right? So we got this here instead. So that's the general solution. And then we have some information. Then what can we do, guys, to find the exact solution? One of the things we could do is we have initial condition, right? So we're going to let T of 0 be capital T naught, right? So put the 0 into this equation right here, and we end up with this. That goes to 1. So the C is equal to the T naught minus Ts. So what does that mean? Okay. This look complicated, but it actually isn't. You just have to learn to read this a little bit more carefully. Okay. So this right here is a Newton's law of cooling right here, guys. Okay. Right over here is Newton's law of cooling. But way that you should think about all this, though. Okay, let me just move this slightly up. Oopsie. Sorry about that. The way you should think about this, it is much a simpler way. Think of the surrounding temperature as the x-axis, right? And that's the initial temperature, the difference right there. And when you look at that, it's a decay, isn't it? It makes sense if you had a temperature that's higher than the surrounding temperature, that it will sort of approach it like this, wouldn't it? Exactly. And the way that looks, if you think about this, is this right here, guys. This is a surrounding temperature that it is approaching right there, but the gap over here is the A that we're used to putting in front of the E. Yeah, so if you visualize this over here, this Newton's law of cooling appears to be much more intuitive. So this right here is the gap of the initial temperature to the x-axis, right? And then it's going to approach that value. So that's what they represent. Okie doke. All right, guys. So let's go do a problem over here, guys. So we need to unpack this question. Let's read it first and try to unpack what this is saying. Okay. Suppose that the police discovers a corpse at 10:23 p.m. That's not relevant at this point, right? And temperature is determined to be 80 degrees. So they discovered at 10:23. So the moment the investigation begins, the temperature is what? 80 degrees. So this is when small t is equal to 0. Time begins then. So this is the value of the temperature T naught, right? So that's important. An hour later, it's 75. So that right there, capital T of 1 is 78.5 degrees Fahrenheit. For the past 3 days, the surrounding temperature has been that right there. So that right there is T sub S is 68 degrees. And more importantly, it says estimate the time of death. How are you supposed to do that? Well, so this is where the common sense comes in. And this will be slightly controversial in that the accepted body temperature, right, is 98.6 degrees. That's not actually quite true. But that is the convention that we in our society say it's 98.6 degrees. So that's what we're going to go with, right? So basically you're asking us to find T when our temperature was 98.6 degrees. So that's what it comes down to, okay? All right, guys, so let's do this. So let's put all the temperatures all together like this. So we have small t, capital T, listed over here, guys, all the important ones. At time 0, my temperature was 80 degrees Fahrenheit. Hour later, 78.5 degrees. And we want to find T, which we would expect is negative, right? Because we have temperature going down this way, and that right there is 80. But we want to know when temperature is what? 98.6 degrees. And that T has to be negative, right? Yeah, you need to keep big picture of what's going on, right? So that's what's going to happen, guys. So we're going to go through the calculations, and here we go. Let me bring up what I wrote down already to speed up the video a little bit. Okay, so you don't watch me write this out. So when you do that, I wrote out the equation, and I plugged in all the appropriate values. And luckily for us, that was 1. It's easier that way, right? So that came out to 10.5 over 12. If you go through the calculation, that's 7/8, right? So it's ln of 7/8 or 0.875. I prefer fraction, so that's what I'm going to be using, all right? So the first thing I did was to find the K value. And the second thing I have to do is put that into the equation so that we know what that is, right? So let me just bring that a little bit higher, right there. There you go. Now, so we're going to find small t such that, oopsie, such that T of T is 98.6 degrees. I forgot to write that out, guys, okay? And then right after that, I'm going to write down all the relevant information, which is, pretend that I don't have this in front of me, right? So TS is 68, the difference in temperature is 12 degrees, and the K is ln of 7/8. So I'm going to plug all that into this equation that we already know. And when you do that, we get this. Subtract 68 from both sides, 30.6 divided by 12, we got 2.55. So we ln both sides, that's what we get. So T is ln of 2.55 divided by ln of 7/8, which gives me negative 7.01. What does that mean? It means that the corpse, the last time we had 98.6 degrees, was 7 hours before the discovery, right? So we expected the answer to be negative, right? So everything's working out great. So we therefore conclude that, therefore, it was 7 hours before the discovery of the body, which is around 3:23. One thing you have to understand, guys, the temperature was measured by an instrument, which means there's an error, either by human or the instrument, because it may not have been calibrated properly. Maybe it's not exactly 68 degrees. It could have been 67.9 or 68.1. The point I'm trying to make is that you shouldn't make too much of the decimals over here. So don't claim greater accuracy, precision than it actually is. So we're usually going to say 7 hours is good enough at this point, right? So 7 hours before the 10:23 is 3:23 p.m. All right, guys, that concludes the lesson for 3.B. and I shall see you in class, guys. Okay, until then, have a good night.